It's with very great pleasure that I'm introducing Simon Peyton Jones to give us his perspective on the coming together of mathematics and computer science in education. Simon has made major contributions to the application of mathematical theory to practical computer language design. Simon's been a very good friend to those of us engaged in classroom research in tenure mathematics and functional programming. Over the years, ATM members have contributed extensively to computer-supported mathematical education. Accordingly, we look forward to a stimulating talk and discussion. Simon.
Great, thank you, Ian. Let me share a screen here and still be able to see chat. Yes, good. Well, it's a great pleasure and privilege to be here. Thank you for inviting me. It's to be invited to address a bunch of teachers of mathematics is quite a privilege for computer scientists. So I'm not a teacher and I'm not a mathematician, though I did 2 years worth of a maths degree at Cambridge. But nowadays, all research computer scientists are basically mathematicians in disguise anyway. Now, Ian tells me that you're I should not worry too much that you'll be sort of sit there like quiet, polite audience, that you're feisty, even argumentative. So please make comments or write questions in the chat, which I'll monitor, and Ian will monitor as well, and maybe interrupt me. It would be more fun for me if this turned into some kind of conversation rather than just a monologue. I have plenty to say, but we will just cut and make sure that we get to the end, and then we're going to divide into breakout groups at the end. Okay, so here's our starting point then. Computing is now has now become established as a foundational subject alongside maths and natural science that every child learns from primary school onwards. This is what the national curriculum says in so many words. It says that all children from primary school should understand and apply the fundamental principles of computer science and should be able to analyze problems in computational terms and have repeated practical experience of writing programs to solve such problems. So that's pretty direct, pretty black and white. It's moved computing from a kind of instrumental or perhaps even vocational subject that you might study somewhat. You might study for the purposes of being able to operate a computer well, right, to a foundational subject that you might study for so that you can understand the world that surrounds you. So and the reasons are exactly the same that we want to study maths and natural science for every child from primary school onwards, namely so that it equips children to have to understand and have agency in and be able to make informed choices about the natural and the digital world that surrounds them. That's why we teach children physics. It's not because they're all going to become physicists. It's because if you know nothing about physics, you are disempowered and unable to make informed choices about the world that surrounds you. And it's just the same with computing. So that's a pretty big shift of perspective. And the question that we want to talk about today is how might that shift of perspective affect the relationship between computing and mathematics? And the suggestion I want to put you before you, which was exemplified beautifully by George's talk earlier today, was maybe we could think of it in a symbiotic way. So symbiosis means when two biological organisms have a somewhat close, intimate, and long-term interaction that enriches them both. That's what I'm after here. So here's a little vignette that features Miles, who is indeed here in this conversation. It's in the audience here today. He was teaching a workshop using Scratch at in London several years ago, and a teacher wrote to him subsequently and said this. He said, this girl M realized that she could replace the repeated steps of a loop which was moving a turtle around and drawing a square. Instead of writing 8 commands, she could write 2 commands wrapped in a for loop that just did those 2 commands 4 times. And she explained this to her colleagues in the class, and she had the confidence to do that. And nobody really told her how to do this. She hadn't had iteration explained to her. She just tried it out and it worked. But what I really like is what this teacher wrote about her subsequent experience. She says, I have M self-esteem going through the roof, and she has associated her computing success with mathematics. Over the last couple of weeks, she solved maths problem after problem. She's met target after target. She's truly flying. And she's doing this because she's had a positive experience of computing. Now, for me, I find this quite touching. It makes my sort of heart feels good. It's that sense of agency and empowerment that I think that we seek both as mathematicians and as computer scientists, and perhaps we're going to get even more by talking to each other. Before going there, though, I just want to highlight two related dangers. One is that we treat maths and computing as being in competition for limited timetable slots, right? That is, we conceive of ourselves as kind of competitors in the challenge of trying to get mind share of children or teachers fighting each other. This is not good, right? Because it's a zero-sum game. And actually, I think we can do better than that. We can, hence the title of this talk. Maybe we can, by working together, we can enrich both of our subjects to the benefit of both. The other danger is that computing is perceived as a kind of useful, yes, perhaps even trendy these days, decoration to the real subject, which is, of course, mathematics, right? So here is a symbiosis between the bird that picks the ticks out of the hide of the buffalo, and that is a symbiosis, but it's slightly unequal partners here. I'd like to think of us as more equal partners in this game. And another thing I picked up from George's talk earlier today was he's saying it's easy to sort of layer computing into the curriculum and just say, well, look, they're doing some programming and they're engaged. Look, it's exciting. But his question was, are they learning any mathematics? So rather than saying we'll do one thing and then we'll spend a bit of time doing something else and look, it looks good and they're engaged, let's try to make the most of this interaction. So what I would like to, the slogan I would like to suggest is that it's not just a way to do maths better, but we might even think of it as a way to do better maths and perhaps to do better computing too. But this is the ATM conference, so let's concentrate on maths. So far, so good. Let's just say a couple of things that I'm not talking about. So one is, of course, there's a lot about how to use information and communication technologies of various sorts to teach all subjects better, right? To use distance learning and flipped learning and use the internet in a creative way. That's all very good, right? It's all and it is important. It's just not what I'm talking about. Much closer to what I'm talking about was Alex's talk earlier today about how to change mathematics teaching because of the availability of computers as a tool. But his emphasis was very much on, we're teaching maths and we're going to change the way we teach maths because of computers. And mine is a little bit more even-handed. So they're much closer, but they're not my primary focus. Okay, so first we have to say a little bit about what we might mean by computing as a school subject. Remember, in that words of that national curriculum, it said computer science. Now, when I was at university, not so long ago, only 40 years ago, computing wasn't even a bona fide university subject, at least at the University of Cambridge. It is now, but it's been quite a big step to think of it as a school subject rather than as a university specialism. I think of computing as the study of information, computation, and communication. Not, notice, data, algorithms, and networks, right? So these are, I'm trying to stress the discipline aspect of the subject here. And I put in sort of smaller writing some of the pieces of that you might think of under these various headings. And I put a box around them all to suggest that programming is a sort of cross-cutting concern. It infuses and is, everything is shot through with programming. Computing without programming would be like natural science without lab work. It would just be hopeless, but it's not the whole thing. So it isn't just about why we should teach our kids to code. It's about the underlying subject discipline. And there are lots of common themes between the study of computer science as a foundational discipline and the study of mathematics. So abstraction is a very obvious one, right? In Alex's talk, he was talking about abstracting from the real world to some kind of model of the real world, and then doing some computation or some reasoning or some calculation about it. Calculation was the word he used. And then finally interpreting that back into the real world. And of course, that's what we do when we write programs all the time. We are abstracting pieces from the real world into our programs. Programs deal in abstractions. Another very common theme is the idea of doing something once, right? With algebra, instead of doing something many times, we write some algebraic equations and we solve, 1 million specific cases all in a single blow. And if you write a function definition in Scratch or in Python, you are parameterizing over the input parameters. You're doing something once rather than many times. And the abstraction that is algebra is quite similar to the abstraction that is a function. And you have variables that stand for values. Both disciplines encourage precision in thinking rather remorselessly, actually, and logic. Logic plays a very fundamental role in computer science, as it does, of course, in mathematics. So there's lots of commonality. Now, but the one that I'd like to stress most of all is that I think of computing as mathematics made incarnate. That is, mathematics takes flesh, it becomes tangible, it becomes concrete, it becomes executable, it becomes experimental and exploratory, as some of George's examples showed, and often it becomes motivated by some kind of context. I'll show you some examples of that later. So here's a slightly, perhaps this isn't a primary school example, but maybe a secondary school example of what I mean by maths made incarnate. If I write a for loop, and I to add up the numbers between from 1 to n, then I've got something that looks very like a base case when I initialize the variable. I've got something that looks like an inductive step when I add I to it. And then if I'm going to reason about the total that this loop computes in any particular iteration, that is what computer scientists would call the loop invariant, all I'm doing is I'm doing a proof by induction. So I think of loops as induction made executable, if you like. So whereas the idea of a proof by induction is a somewhat abstract thing, somewhat sophisticated thing, and yet primary school children are in effect doing not exactly proof by induction, but they're doing inductive reasoning and execution from a very early stage. Nothing in the chat so far, very ominous. Of course, I'm not the only person to have thought these kind of thoughts, right? Everybody is thinking about this. The question is just how do you turn this into reality? So let me just give a few pointers to some other people who've done some brilliant work in this area. One is Celia Hoyle and Richard Noss's work on Scratch Maths, which I think many of you will come across. The URL is here in the slides. I like this, the way that they put it. Can we find a different language, that is a language different to the language in which mathematics is usually expressed, a different language and a set of ideas and approaches that is somehow more open and more accessible and more learnable, and that somehow brings mathematics to life without downplaying the mathematics. The mathematics is still the goal, right? But it's maybe just expressed in a different language and a different sort of way into that cognitive space. Here is they have a very nice video on the Scratch Maths homepage, and I love this quote for this young woman who's describing what she liked about participating in the Scratch Math project. She said, what I really like about Scratch is when you press that start button and you see your script come into action, it's like magic in front of your eyes. And here she didn't mean the sort of magic that Arthur C. Clarke was thinking about when he said any sufficiently advanced technology is indistinguishable from magic, which I take to be a bad thing, magic that is not under my control, made by somebody else. Here she meant it's sort of miraculous that something that I did and that I understand does something so wonderful as draw these patterns. It's sort of, I found it very inspiring, this little video. You should watch it. So that's Scratch Maths, and Scratch Maths is back with a whole bunch of, it's a primary school kind of level, and there's a whole bunch of actual tangible materials that you can try out, and I hope that if you haven't come across it before, I hope that you will. Here's another, which is perhaps a little bit less well known in this country, which is the Bootstrap World project, and it has 4 major units on algebra, reactive programming, data science, and physics. And there they're using, each of these is a pretty substantial strand. And they're explicitly targeting learning maths. They're not targeting learning computing. They learn a lot of computing on the way. And here, they're explicitly exercising mathematical concepts like coordinate planes, ratio and proportional, domain and range, function composition, that kind of thing. Okay, so they're very explicit about the connection with mathematics. And it's been extensively trialed in schools. These are all projects. These are not just academics, polishing their fingernails. These are people who are working in schools. Paul Curzon I wonder whether you all know Paul Curzon. He's an amazing computer scientist, works at Queen Mary College in London, but does a lot of work with schools. He has a wonderful magazine called Computer Science for Fun, CS for Fun. It's a website and magazine. And he has a whole page here. I give him the list above it, but that the URL here that describes how computer science and maths, and in particular numeracy, has a lot of examples about numeracy, can interwork with each other. Then from this very conference, George's talk this morning, I thought was a brilliant description about how, if we think of computing and maths in symbiosis, it might change how we think about teaching mathematics. I picked this little piece from one of his slides, that the learning is it's kind of exploratory. You write an executable program and you keep changing bits of it, and you explore in ways that would be hard to do with a pencil and paper. He described it as playful, and also that there's a lot of incidental learning going on, that rather than just teaching saying your learning objective is this, you're just learning by trying things out, not in the completely unconstrained way of just be in a big room full of bits of kit and have fun. It's quite directed, but there's quite a lot of incidental learning going on. I just put in this thing about immediate feedback, because I think this is also pretty significant. I'm not a teacher, so you're better judges than me, but computers are very pitiless about pointing out your mistakes. They do not say, "Ooh, I better put this tactfully," that you have written a bug in your program. No, it just doesn't work. But at the same time, it's private and it's non-judgmental, right? The computer doesn't say you're a stupid person, and it's not a public humiliation. So you get a very tight feedback loop, but in a very non-judgmental kind of way. Ooh. I'm not going to respond to Emiko's question yet. We can maybe do that in the panel discussion. Do you agree that computation is limited by mathematical logic and therefore artificial intelligence is not possible? It's a very open-ended question. Thank you, but maybe later. Yes. And Pip, I do agree, Scratch is tremendously useful in secondary beyond. We should not regard Scratch as being, just for babies, just for primary school students. It totally, if you do it in Scratch, you probably should do it in Scratch. It's so immediate. Now, I wanted to give bring this down to earth a bit I was challenging myself really to come down from these airy aspirations to something more tangible. So here are 3 tangible examples, which I'll give in successive levels of detail, just to give you another idea of what I, from a computer science point of view, am thinking about. But with the caveat, of course, that unlike these other projects that I've described, I'm not a school teacher. I do not teach mathematics. I do not work in a school. And so you will just have to make of this what you will. However, this one comes from an interaction I had with my 9-year-old son Kenzie, and who was doing some Scratch programming, and he said, Dad, I want to make the rocket go towards the planet, but as it gets closer, I want it to slow down. So this wasn't terribly hard. We did it together. Here's how you might do it. You want to move the rocket successively. There's the forever loop with a little gap in between. That's the wait 0.2 seconds. And we'd like to move it. How many steps? Oh, the number of steps we want to move is something to do with the distance between the planet and the rocket. So we need to subtract the distance of the planet, the x position of the planet, from the x position of the rocket. And then maybe to choose how many steps we go, we then have to scale it by something like, and here I divided by 10. So of course, this is kind of second nature to all of this, but when I started to think about it, I realized that already in talking to Kenzie, without having to have learning objectives and things, we'd already discussed coordinate geometry. This was just in one dimension, in fact. We'd already discussed sort of grouping, right, that the subtraction occurs before the division, and scaling, but he had to have some notion of proportion to scale it down. And also, if the rocket was on the other side of the planet, I think this came up in George's talk, then you'd have a negative difference. You'd have, so the numerator would become negative, and it comes up. It's almost as if the child begs you to allow negative numbers, rather than us having to say negative numbers are what your learning objective for this lesson, right? I would like mathematics to be something that children are begging us to say, of course we must be able to do this, and you say, sure, and you can. Here is one other piece that barely came up when I was talking to Kenzie, which is that when the rocket gets close, so that the number of the distance between the two becomes, round about 10 or a bit more than 10 or a bit less than 10, then you have to start talking about, well, what is 9 over 10? How many steps is that? And can Scratch talk about 9 over 10, or will it round down or up? And you get the things which computer people think about a lot. Now, let me just look at these. There's lots of commentary here. This is really good. Thank you very much. Okay, but I think none of them look like formulated in the form of questions, so I think I'll carry on. Let's see. Then we try to do this in 2 dimensions, and I realized again, this was a learning journey for me actually, that so now I've got to move on a diagonal way. But of course, I know that I can just do the X and the Y separately, but it was a bit of a surprise to Kenzie. I don't know whether he really got it, but the idea that we can just think about the X displacement and the Y displacement sort of separately, and they'll add up in a sort of vector-like way to the right thing, that's quite a sophisticated idea. I don't quite know when the right cognitive moment to bring this in, but I just thought there was quite a lot of places you could go with this. And indeed, we didn't get onto all of this stuff, but you can go a long way with this kind of game. You could involve mass and velocity. You could think about the inverse square law. Rather than going slower when you get closer, you could have an inverse square law. You could have that should be 3 body problems, and have planets orbiting around themselves, and they can draw where they've been very easily. You could have a spreadsheet that gives a table of position, velocity versus time things, and graphs to visualize that. But what I like about all of these things is they're things you can just try out. You can just try it. Yeah. Okay. I will, by the way, people who are interested in links, I will post all these slides via Ian towards the end of the day. So that's example number 1, primary school level. Example number 2, this is more of a sort of early secondary stage. This is how would you estimate the value of pi? We do areas of circles and pi r squared and all that, but when I did it at school, it all felt a bit abstract and remarkable. And there's this funny formula, and you just operate the formula, and lo, I become an excellent formula execution device, right? I'm the algorithm that executes pi r squared, but I didn't really understand it at the time. Here's one way which you might understand it. Imagine drawing a unit square here. Well, this is a sort of 2-unit square around the origin, and a circle that is inscribed within it, and throw darts at it. Well, and what proportion of the darts fit inside the circle? Well, of course, the area of the green circle is, if you just look at it intuitively, it's going to be, a bit less than 4 times r squared, but 4r squared is the area of the whole square, so it's a bit less than 4. So you can see that pi is going to be kind of round about 3. And then the proportion of the darts inside, well, it's going to be pi. You have to know the formula for the area of the circle. Okay, pi r squared divided by 4r squared. So that's pi over 4. So how could I then calculate the area of or maybe sample the area of the circle? So I did, let's see, I made this little spreadsheet. It took me about 5 minutes. Here it is. And lo, so what did I do here? Well, these, the first column is the x coordinate of my dart. The second column is the y coordinate. They're both going to be random numbers between -1 and +1. And the inside circle column here is a formula that says, did the dart land inside the circle? And then at the top here, well, I'm going to is the computed value of pi. So I'll just show you the formulae. Here are the formulae. So rand in Excel computes a random number between 0 and 1. So to get it between -1 and +1, I had to double it and then subtract 1. So there's an interesting little piece there. So then I do lots of those, and then this is my calculation. This needs Pythagoras, of course, to figure out whether my dart landed inside the circle. And in fact, I decided I didn't need to use square root, because if I take the square root of both sides, square root of 1 is 1. And then I just copied down. And what's this formula up here? That formula just tells us I'm going to count the number of times I get true, right? Because it's true if it lands inside the circle and false outside. I'm going to count the number of trues in this, in this 100 cells. So I've got, C1 to 100. I've just copied down, done a lot of them, and divide by the number of rows in C4 to C100. And then I multiply by 4 because that was the pi over 4 bit. And lo, so now we go back to here. And every time I hit refresh, so I'm secretly typing F9 to recalculate every time. Every time I recalculate, I get a different value. Oh, that one's not very close, 2.96, 3.17, 2.96, 3.25. Okay, and then I might think, well, maybe I could get a better estimate if I used more rows. So I think I copy pasted 800 rows. I have to look down to check, but I think I've got that right. And now when I recalculate, I get value that quite a bit closer to the right answer, more of the time. And I, on the in this little visualization here, I'm plotting, or at least a sample of the points that I've done. And that also is a kind of very quick thing to do. This whole thing takes about 5 minutes to put together. So what am I trying to share here? Just that, let me go back to this game. Just that I'm trying to illustrate a sense of symbiosis between computing ideas and maths ideas. So you could think with a maths hat on, you might think I'm trying to learn about pi, or perhaps about statistics actually, about how many values I might need to get how close to pi. But also from a computing idea, I might like to think about, I'm learning some incidental skills about how to use spreadsheets. I was flipping between formulae and values there. I don't know if you saw that, but that's something that's quite useful to know. Here in this spreadsheet, I've also got the column C has Boolean values. So we're used to seeing, well, in Scratch, you're used to seeing things like, if X is bigger than Y, then do this, otherwise do that. But here I'm computing the inside or outside as a Boolean value, true or false, right? It's a first-class values. And indeed, to computer scientists, Boolean values are first-class values. But I think it takes a while, even for university students, to truly get a hold of that. But there it is, manifested as a cell, as a value of a cell. So there's a lot of stuff going on in this one little exercise. I think it's could go. I think you could go fairly far with this. So that was a second example. Oh, I need to redisplay the chat so I can see if anybody what anybody's saying. If anybody, let's see. Jeffrey asked, you're using geometric ideas. How do you see geometry being part of computing? I think I think I'm probably the wrong person to answer that question. I suppose I see being able to visualize things seems super important, right? That's I'm often asking people when they're in a research context to draw a diagram or to give an example. So, and if you, but I'm not sure that visualization is coterminous with geometry. If you mean specifically geometry, I think you need to ask somebody other than me. Alison says, this activity feels as if it belongs equally well in a maths or computing classroom. Yes, exactly. That's the whole point. The hypothesis I'm exploring is that maybe we won't have maths classrooms and computing classrooms. Perhaps we should only have classrooms. Right. And at primary school, of course, that is the case already. But maybe we think of, oh, today we're doing maths or today we're doing computing. I would like to say today we're just doing maths and computing. And maybe at key stage 3, all the way up to age 14, when we start to separate into GCSEs, perhaps we could, wouldn't it be great if we just had maths and computing classes? We did not have maths classes and separately computing classes. Even if it takes longer, there are lots of learning going on when making it. Yes, and here the question is, will it really take longer? I don't know the answer to that. I think there's a lot of research to be done here. My hope is that in the end, it won't. Okay, lots of good conversations going on here. I'm going to carry on. I want to give a third example. So this third example is a very different, I'm going to spend longer on this example because it's a less familiar one. And my first example was kind of primary school level. Second was probably secondary. Well, certainly secondary, but perhaps key stage, late key stage 3, early key stage 4. This third one is perhaps more A-level, though I think a good Key Stage 4 class could totally go with it. So it's about machine learning. Now, Alec gave an example in his talk about using Wolfram Alpha and its ability to build image classifiers. So here he had a magic box, and for him it was a magic box that will take images and spit out, classify them into who. So here I've got a really simple classifier that is only determining whether the input picture is a picture of Hermione, right? And it will say yes for the first, and it will say absolutely not for the second, because Alec looks nothing like Hermione. But the question is, how does the magic box work? And that's what I want to get at for a little bit. So I'm now going to dive into a particular example that you may be much less familiar with, and hope that you'll enjoy it. So here's a smaller example. Suppose I want to make a magic box that predicts the quality of a biscuit recipe. And my biscuits are going to be made very simply. They consist of X kilograms of flour, Y kilograms of butter, and the rest is sugar. I mix them together and I bake them. I get biscuits, right? And then I'm going to feed them to my children and see what they say. Is good or bad? Right. So in the end, I'm going to produce a sort of chart like this that says I'm going to have a table with on the right here is the data in my table: amount of flour, amount of butter, and the balance is sugar, and the verdict is good or bad. And then I'm going to plot the good or bad. I can imagine plotting it on a two-dimensional plot, and if I'm lucky, they'll all cluster together like this. And I want to learn from the data which are the good biscuits and which are the bad biscuits. So if I have a new XY pair, I can predict what the answer is going to be. That's a simple version of this. Right? Let's scale up a bit. And one way to do it, the simplest way to do this kind of thing, is just to suppose we could learn a line that separates these two clusters. Well, what does it mean to learn a line? Well, we know that lines, we're mathematicians, right? We say, what's the equation of a line? Y equals ax plus b. We could just learn a and b. Could we learn the values of a and b that describes a line that separates these clusters? Well, that turns out not to work very well, because it doesn't work very well when the lines are steep, right, or even vertical, because then A gets too large. So it's kind of better if you can define your line by this equation: ax plus by plus c equals 0. Right? That's an equation that also defines a line. It has 3 parameters, but none of the parameters go to infinity. And in fact, it's very nice, because if A is 0, you get horizontal lines. If B is 0, you get vertical lines, and C sort of moves the line, displaces the line around. So this turns out to be, this is already an interesting observation, that we can describe lines in more than one way. Okay. I'm guessing x plus y is less than 1. Yes, Miles. I should have said x plus y. The balance is sugar. It's only 1 kilogram, so x plus y had better be less than 1. So I'm going to try to learn A, B, and C. And the good biscuit's going to have the property that ax plus by plus c is going to be bigger than 0, and the bad ones, they'll be less than 0. And indeed, here's an yes, there's indeed a possibility that you could find the distance from a point to the line, right? Because you might hope that the further away the line for it, the more confident you were, and you could do a little bit of mathematics to determine the distance away, but that's kind of optional. But basically, the idea is we're going to make some kind of magic box that has parameters A, B, and C, that has the X and Y coming in on the side, and that spits out yes or no, or a number, because we're going to spit out a scalar value, the number which, if it's positive, good biscuit; if it's negative, bad biscuit. The larger the number, the further it is from the line, the more confident we are in our prediction. Okay, so the question is, how can we adjust A, B, and C based on the data until we get as good answers as possible? That's the question before the house. So what do we mean by as good answers as possible? Well, we want to minimize the number of mispredicted biscuits in the training data. Of course, so training data there might be some noisy data or just bad data, so we might not be able to drive it to 0, but we want to minimize mispredictions. So here's what we might imagine doing. I'm going to show you this. What we'd like to do is to, you could imagine starting with a line, a random line perhaps, and then sort of picking a mispredicted biscuit from the training set, that is from the data of experiments that I did on my children, and adjust A, B, and C to somehow tug the line to be mispredicting less than it was, as it were, tug the line towards the biscuit that's being mispredicted, and then just keep repeating that. And I want to show you that in action. This is something, a little website that you can all go to, and I hope you will. I'll give you the URL in a second. It's called TensorFlow Playground, and it has a let's see if I we start here. Here are the biscuits, just as I showed you, clustered in the way that I showed. And you, it's got this little box here is the magic box, the thing in the middle, the one neuron in the middle. And if I press this big play button at the top left here, it then somehow does that procedure that I described and finds a line that separates the biscuit. And if I can stop it and start it again, and I'll get a slightly different line. And you can see there's it computes something called the test loss. The test loss is essentially the number of mispredicted biscuits. The training loss, which you'll see written just below, it keeps some of the data aside. So it trains on some data, and then it has some data kept aside that it doesn't use for training, and it used for testing to see, did the training work out well? That's what's called training loss. And if the loss is 0, it means no mispredictions. That's really good. Okay, so TensorFlow program. I'll give you the URL back in the slideshow. But you can start off right now. You can start off playing with this. What if you get bored in any of this talk? Okay, so I'm going to switch back. Where do we go? Yes. So here is the URL: playgroundtensorflow.org. Maybe somebody can put that in the chat so that anybody who's missed this catches it. Okay. Now, how are we going to do the tugging business? Well, we want to, if we got a mispredicted biscuit, the output should be positive, but actually it's negative. And I want to adjust A, B, and C to make the output less negative, more positive. How do I do that? Well, one simple idea would be, maybe we can adjust the parameters most by choosing which parameters most strongly affect the result. Now remember, the result R here is simply AX plus BY plus C. That is the thing we're computing. That's what the magic box does. That all it does is compute AX plus BY plus C. Yes, in fact, I drew it inside the box. That's it. That's what the computation it performs. And so how would we adjust A, B, and C to drive the output a bit more positive? It was supposed to be positive and it was actually negative. So we want to think about how sensitive is R to changes in A, right? That is, we want the partial derivative of this expression with respect to A. And if we take the partial derivative, I mean, I've written it out in mathematical notation here, but actually it's fairly obvious that the sensitivity of R to changes in A is simply X. And the sensitivity of R to changes in B is simply I want to be able to see the chat. The sensitivity of R to changes in B is Y, and the sensitivity of R to changes in C is 1. Does that make sense? I hope that somebody's going to start asking questions if this, but you're mathematicians, so I'm hoping this is like your mother's milk. So how could I turn this little piece of mathematical reasoning into, well, an algorithm? Well, here it is. I want to adjust, I'm going to successively, each time around, I'm going to adjust A by an amount, if I change A by an amount that is described by its sensitivity to the output, the sensitivity of the output with respect to changes in A. So since I decided I'm adjusting A in proportion to X, B in proportion to Y, and C in proportion to 1, how much do I adjust them? I need to have something called the alpha, which is the learning rate. Right, so maybe alpha is a small number that would adjust things slowly. If it was a bigger number, it would adjust things fast. Maybe I want to start off with a big learning rate and decrease it. That's a piece of black magic that goes into machine learning. And so this is what you do every time around the loop. This is the whole machine learning algorithm. This is what is going on inside, the classifier that Alec presented us with this morning. We pick random initial values for A, B, and C. We pick a mispredicted biscuit from the training set. Then we adjust A, B, and C using these equations, right, with a particular fixed value of alpha, and then we just iterate. And that's it. That is all of machine learning on one slide. The core algorithm of machine learning. This step 3 is called backpropagation. Now, of course, the reality is always a bit more complicated, but this is the essence of it, and it's incredibly simple. So if that was it, then I mean, you might think it has to be more complicated than that, right? Oh, what about if the data isn't separable by a line? Like here's some data that is, there's no line that separates these. Well, you think maybe I could still learn to separate the good biscuits from the bad biscuits by using more lines. So here's how I could use more lines. I could maybe take two magic boxes to compute here P and Q respectively, each with independent parameters A1, B1, and C1, A2, B2, and C2, and somehow combine those P and Q together to make the final output R. Maybe that would somehow, I mean, so I've computed two lines here, that's the P line and the Q line, and then I said somehow vote, didn't I? Right? Somehow vote together. Well, how could I combine two things? Oh, I've got boxes that do that. Maybe we should use the same kind of box. Huh. Maybe that could just be another box. And now I'm looking at the chat in the hope that somebody is going to say something that is blindingly obvious in retrospect, was completely obscure to me in prospect. Why would this could not possibly work? This cannot be an improvement over what we had. We just have to use some mathematical reasoning. Look, here's a big box that has sort of 9 input parameters now, but it's still a big box with 2 inputs and 1 output. But if we compute what the outputs are, just using, you know, ordinary algebra, R is A3 times P, B3 times Q, and then do this. Well, look, crumbs, it's still something times X and something else times Y plus something else. It's that big box was the same as a little box, a single box with 3 different parameters. So anything I could learn with this three thing box, I could learn with a 1 box. So, you know, total disaster. You know, this is not a step forward. But I love the way that seeing that it's not a step forward just involves elementary, you know, key stage 3 level mathematical reasoning. Okay, so what can we do? Well, in fact, the trick that you have to do, and this is the second key trick of machine learning. If you remember only 2 things from this talk, the first thing to remember is this is how backpropagation works. And the second thing to remember is this is why we need nonlinearity. You stick on the output of these boxes, you can stick a nonlinear function. A very popular one is called ReLU, which stands for rectified linear unit. It's an incredibly simple function. It's 0 if its input is less than 0, and it's linear otherwise. Hence, the linear part is for the greater than 0, the rectified bit is the less than 0. That's all ReLU is. And then you feed that into this other box. And that turns out to be enough. Let me show you. Let's go back to TensorFlow Playground. Now, so let me show you some more things you can do then with TensorFlow Playground. You can add layers here. Let me stop this. And let me pick the more difficult example here. And of course, if I attempt to do it with this one layer, it tries to learn a line, but it's really not doing very well. You can see the test loss. The test loss is bad, right? 0.4 of all the input test things are not being well predicted. The training loss is for some reason training loss is bad, 0.4. Test loss, unsurprisingly, is a little bit worse. So what to do? Well, what I said was we add an extra layer. So let's add a layer. Here, let's add a layer. And let's have a couple of layers here and maybe one here. So this is with only two boxes, right? Let's have a try with that. Oh, well, it's kind of spooky, isn't it? It gives somewhat better. And at this stage, you start to play. You think, hey, let me just add more. You know, how about adding more boxes here? Does that help? And let's make, oh, spookily, it does. Look at that. And these little straight lines around the edges of this region in the middle, those are each computed by one of these little guys. Look, they're each computing a different sort of line across. This one looks as if it's not doing much good. These ones are all computing lines and they're somehow voted together here. Isn't that cool? You think, maybe what would happen if I made this a bit harder? What would happen if it was like this? Ooh, would that be good enough for this sort of, having a bit more trouble here, aren't we? Somehow, the way the data is split up is not so good. Maybe at this stage you can go wild. You think maybe I should have some more layers, and maybe they should have some more neurons in them, and then you could just sort of press go. And I have to tell you, folks, this is what machine learning people do. They do a lot of suck it and see, and miraculously, it does pretty well. Training loss, very, very good. And this is you now know everything you really need to know about machine learning, and you've done it in 15 minutes flat. Okay, I'm going to wrap up. Just let me say that up here, learning rate. Do you remember that alpha parameter? You can change the learning rate here. That was that alpha guy. The ReLU is one of the things you can pick here. There are some others that you can pick, tan H and sigmoid, but linear, I think, is the one we started with, where there's no non-linearity, and sure enough, it doesn't learn a bean, right, as we discovered earlier. Okay, back to things, but I'm going to wrap. Oops, yes. Okay. Right. So I just want to finish up. I want to also be able to see the chat, which I can't see at the moment. Yes, I can. Good. Oh, Miles says, is there any way to automate the suck it and see bit? No, Miles, there isn't actually. All of my colleagues at Microsoft Research are doing a tremendous amount of sucking and vast amounts of compute power getting taken, just doing essentially experimental exploration of the design space of their various neural networks. It's quite, I mean, there is a lot of systematic thinking, of course, a lot of systematic thinking, but there is no, there's no completely systematic way of saying, I know that the way to do it is this. There's tremendous amount. It's like the early days of experimental biology, in which people were just discovering things in the natural world and classifying them, arranging them into trees and figuring out a bit about how things work, but hadn't yet figured out DNA. Now I want to wrap up, because I do want to leave time for discussion and questions and breakout groups. So the opportunity, as I see it, then, is to try to see computing as a school subject, not as a competitive upstart to mathematics, but rather as a kind of distinctive lens, a way to think about maths education that lets us see it in a new light. Now, Alex examples used computing in the service of maths. You might think this machine learning example is using maths in the service of computing, and some of the earlier examples were perhaps more symbiotic. You know, it was more even-handed. I don't think it needs to always be, but I would love to have, you know, a single conceptual, you know, subject almost, that in which you had examples in which the boot was on each foot alternately, and you were always marching in parallel, that you were each was shedding new light on the other. And I don't think that need upset maths education. I think more, and this is also in the theme of Alex's presentation about computer-based maths, more helping maths education find its true identity, find the essence of what a good maths education is really like. And this is my final slide then. To make 1 and 1 make 3 then will not be easy, I think, because it will inevitably reshape the curriculum of both subjects. Actually, I think in George's talk and in Alex, we saw ways in which we can't just take an existing maths curriculum and say we'll plow through it in the same order and the same things, but we'll just, you know, put some computer decoration on the top. We may need to change the sequencing, and I'm not an educationalist. I don't know, you know, what would be appropriate and what wouldn't. But perhaps, you know, that when I was talking about negative numbers with my 9-year-old, I want, you know, maybe negative numbers or coordinate geometry might occur earlier than they would otherwise do. Because the computing applications that we're using to illustrate beg for them. So it may reshape the order and the structure of our curriculum development. I do think it needs classroom research, something that I know that ATM is keen on, and does a lot of, because it's no point in us doing this in airy-fairy ways in universities, still less in industrial research labs. It has to start in the classroom. If it doesn't make sense there, it doesn't make sense, right? We're trying to actually produce education that leaves children feeling excited and enthused about what they're doing. And most particularly, it needs educators who are interested in both subjects. And this is, to me, this is the biggest challenge, right? it's not hard to find educators who've thought deeply about maths, or it's a bit harder to find educators who thought deeply about computing and computer science. It's really hard to find people who've thought deeply about both. And yet we want actually every teacher ultimately to have that sort of joined interest. And that is a place where I think and hope perhaps that ATM as a group might play an important and helpful role, because you're already geared up on all of this stuff. And I just want to finish with to remind us that this is all not so much about education, it's about our children, right? That we want them to be engaged and curious and creative and playful about our subjects. And we want them to see them as exciting and enriching, not as a dull treadmill. So let's stay connected with that. But I'll go back to this and invite more questions and feedback. Ian, have you been gathering any questions?
Well, there are some which I think we should perhaps take in the panel. John had a question about generality, which is probably more than a second to answer. But if we refer questions now to the panel, and I can briefly introduce the breakout notes.
Yes, okay. Should we just see if anybody who's let me see, I'm going to stop sharing so I can get my video. Has anybody got anything they'd like to add or comment, or indeed ask just quickly now before we switch to a breakout sessions? You could just unmute yourself and dive in. Oh. Okay, well, maybe we should do breakout sessions, but I'm shocked by Ian assured me that it would be difficult to keep the ATM audience down. Well, okay, Ian, over to you.
Just to introduce the breakout notebook that you've hopefully downloaded now. What we did was we took a high-level view, 50,000-foot view of what mathematics and computer science have in common. As John points out, the search for generality continues in the higher and higher levels of abstraction. And then we brought it down to key stage 1 to 3 with algebra and coding, key stage 2 to 4 with data science and modeling, key stage 3 to 4 with reasoning about diagrams, and key stage 5 to college with reasoning about matrix algebra and its applications. For people who prefer to engage with the material through a puzzle, this is a tiling puzzle that we've used with key stage 1 children, and it is a set of puzzles, but it takes you on a journey through problems that have algorithmic solutions to problems which have mathematical solutions but not algorithmic solutions, to make the distinction between mathematics and computing clearer. The notebook also has activities which we've selected from the sessions in the CTM strand, and there's a question in it which Simon would like you to consider. Simon.
Yes, so this is really the question that I was sort of was running right the way through my talk. I would love your help in fleshing out examples of, I gave you 3 examples at different sort of different age ranges for how I could imagine computing and maths existing in a sort of richer symbiosis, but I would love to have more examples. Because I think it's all very well being aspirational. We need to be concrete. So if you could talk, individually or talk among yourselves to develop examples or contexts, or in which you could explore true symbiosis between maths and computing, that would be really helpful. I think if we have a big gallery of such examples, will make the whole story much easier to tell. And I think Ian and I wanted to, because we're in breakout groups and we don't have an easy way to get back together, we wondered if you'd be willing, this isn't something that, as I understand, you normally do in the in-person ATM conferences, but if each breakout group was willing to send, one member of each breakout group was willing to send an email to Ian to summarize a bit about what went on in that group, that would give us some way to connect ourselves back up, and also perhaps to provide some raw material for the panel discussion that's taking place at 4 o'clock. So this isn't a formal requirement, it's a very informal one, but we'd love you to take advantage of it if you are willing. So see if you can find a willing rapporteur. Thank you.
Okay, you've got 8 breakout groups with 12 people or so in each one. I look forward to seeing you at 1600 in I5 or getting emails if you can't attend. Thank you again, Simon, and thanks for joining us.